All right. Let's get started then with lecture 15 on mapping. Oh, we have a comment here. Yes. So the comment is, yes, what was happening under the hood on MROP? Well, there were comments on this, but I guess not enough. There was always the option of looking at the source code, but that was probably not trivial to do. So then let me ask one question. So what would you prefer, to have more help or just writing the adjacency by yourselves? I mean, to have more help on using MROP, probably with more comments, even more, or maybe some examples, or would you prefer doing the adjacency matrix by yourselves?
If I may suggest something, so I think this problem set was very balanced because there was like, you know, how to structure the whole SAM algorithm, not like diving into the details of the matrix and stuff. But I think for the future, you may add like another task of like replacing some functions that you already used in MROP and by your own. So you have the best of both worlds.
Okay. Okay, yeah. So just for evaluation, you mean?
Not for evaluation, like, okay, for the first part, you already understood how the structure goes, like the steps, how to construct this, how to add nodes, how. But after this, you don't know what's happening under the hood. So maybe you replace one function by your own, or replace like create a Jacobian by your own, create adjacency matrix by your own, because you already understood the structure. Now you can dive deep into the details.
Okay, I see. Yeah, maybe, and then you spend more time on just looking at the effects of, you know, several things. Yeah, I think that can be. Okay, more specific examples probably will be good. Yes, that's why we did seminar, but I think it was maybe a little too late. So we did this seminar on 3D, but yes, I think it was. Okay, thanks. I really appreciate your comments. I mean, all things like might be work in progress, especially if you want to do a little more, you know, kind of more challenging things. Maybe this is also more challenging to do this properly. So yes, okay. Yes, sometimes help is not clear. Yes, I agree. Yeah, so maybe, yes, I'm thinking on changing. What do you think? Changing the seminar for lecture 10 or lecture 11 when we start talking about factor graphs and all this, and just give like another example a little easier, maybe. Okay, we will take note on all this. Thanks a lot for the feedback. Now let's get back to today's lecture. We are going to be talking briefly about mapping. So this usually was a lecture we were doing. Oh, it's working, yes. This was usually a lecture we were doing, like explaining occupancy grid map, but we will see that we can expand this topic and just do like a brief introduction of more modern techniques and where these techniques come from. And well, basically, I hope that with this, you will have a little more comprehensive idea of other works, now publications that are just being used. But let's start with the initial definition, right? Always we start with this probabilistic perspective. So if you remember in lecture, the first lecture, we were defining like what are the definitions, the probabilistic definitions of some of these problems. We started with localization. Maybe let me try it here. So the problem on localization was just calculating the current state. So we call this a belief, given some observations and given some map. Well, kind of. We know that this is only for the last time step. Now, the order is a little different, right? So what is given is all these observations, right? It could be from laser, LiDAR, it could be from cameras. The observations are still general, right? So we don't really treat them like just for only one kind of observations, but in general, any sensor. And now what is giving is this trajectory, right? So now this looks a little strange because we have to spend all the course just calculating where we are, right? What is this trajectory, either for localization or later for SLAM? The solution most of the time was calculating where we are, right? So now for doing mapping, what we require is to know this position, right? So what is the way of calculating this? So for now, let's assume that either this is given by some other need, or maybe this is calculated previously by solving a SLAM or, like a window-based optimization or something like that. But this is the entry point, right? So position is known. Let's also consider a little what this map is, right? So we started just defining landmarks. So this was our map. It was easy to define. So landmarks are just positions in the environment, either 2D, 3D. But our map at the end was just a result of, it was just a set of different landmarks, right? So now, just to get an intuition of what's going on, it's good enough. But maybe we can define other maps, right? That can be a little more interesting. I don't know, just to give a little more detail about the physical properties, I don't know, of some environment, instead of just being landmarks, which they don't have obvious connection, right? So between landmarks, what is there? Like empty space, a lot of objects. Are they dynamic? Are they static? So maybe there's other map representations. Of course, there are, but we are going to briefly introduce some of them, right? So why is that? Because maybe what you want is to use this map for other tasks. It's not just to localize yourself, in which case you don't need landmarks. You want something a little more detailed. And then with this, you can do other tasks, right? Or maybe you want a better localization algorithms, right? And for this, you need more precise localization. So it's not clear why this is going to be like the design choice, but definitely let's discuss a little other options, right, that we have there. Okay, so broadly speaking, we have like two kinds of map representations. If you want here, we could be putting here landmarks, right, which belong to the explicit maps. So right, in this kind of class on explicit maps, what we have is that we are specifying like particular instances of the environment, such as landmarks, as we were saying, maybe lines, maybe corners, right? But we need to define them explicitly. So another example now, if we go to 3D, it's surfaces, meshes. Let me give some example. I'm going to try to plot something. So we are now, I don't know, in this room, right? And I'm just going to do the example of, okay, we have here a two-dimensional LiDAR. Okay, maybe this goes like this. Yes. So in this case, what could be our map, right? So if we start with this, we could be saying, look, this is a set of lines, right? Or a set of segments, and they are connected this way. So when you get an observation, you are just going to be updating your lines with respect to these observations. The other definition could be the following, right? So here what we see is that we have corners, right? So we could be saying, look, our map, it's going to be the corners in this two-dimensional space, right? And then we will forget about anything else, and we are just going to be tracking these corners, right? And in this case, these corners could become like a case of landmarks. If we move to 3D, then in 3D, we could have surfaces like, I don't know, planes or other second order regular surfaces, or we could also be just using a mesh, right? So we have a detailed model. This is our map. Maybe we have CAD model for, I don't know, some engineering piece, right? And what we want to do is just localize with respect to this. So maybe we can have access to these detailed plans of some object, right? So, but still, for all these approaches, what you need is explicit information about the object, right? So maybe here what we have is 6 landmarks, 6 corners here, but I don't know, in other cases, we have millions of them, right? So with explicit, you need to explicitly define all of them, right? Now let's go to the second variant, which is a little more flexible, right? So these are implicit maps. We have discussed briefly on the last lecture a little bit about a very popular representation that is point clouds. So what is the great thing about these implicit maps is that you don't need to define explicitly like, oh, okay, here we have a feature, here we have another thing. You just have like, in this case for point clouds, standard set of points, whatever they are. They can be more detailed, less detailed, but still there's not explicit definition of what this structure is going to look like, right? So getting to the same example, I don't know, maybe, okay, maybe this is the map representation of our room, right? So we have here a bunch of points in 2D, and this is it. There's no connection between, I mean, then we could be doing this, but there's no connection between points. They are just a set of points. Another interesting structure that we are going to be talking today about is grid. So usual grid, you just take your space, right, and just discretize. Equal intervals, irregular intervals, doesn't matter. But you should have like some grid structure. And then this is kind of a brute force approach. So we are just dividing the space into small cells inside the grid. And then with this, we can have a more general definition of what it's going to be inside, right? So we are going to be discussing a little about this. We also have surface, we'll see later. Voxels, I'm going to define the letter of trees, which is, and then sign distance functions, right? So let me explain a little more with images, like what are these implicit maps look like. So this is the point cloud, right? What we see here is probably thousands of points. Each of them, I mean, it's colored. In this case, they are colored, right? So it's possible not just to define the geometry, but it's also possible to define well, photogrammetry of the scene, right? So here we'll have like both things. So we have a point and it could be colored, but still it's a point with no dimensions, right? So if you have a lot of points, you can assume that you are going to have better definition or representation of the scene, but that means that you have more points, right? So there's always a trade-off. Now let's see this example of voxels. This voxel was just calculated from this point cloud exactly. What it's doing, just for you to get an idea, do you see that this is very regular, right? So inside voxels, what they are doing is they are discretizing this space, right, into cells. And then each of these points corresponds to the average of all points inside the cell, right? So with this, we are displaying less number of points. Still, this is some sort of point cloud if you want, right? But it's not exactly like that because there has like some regular structure. And well, this is used in some of the techniques I'll be talking about today by the end. But yes, basically we have lots of variants now. We are entering more in the 3D graphics perspective of this. But well, just have in mind that yes, the topic goes deep, right? So there's going to be other representations probably that I didn't talk about. Okay, let's go to the next one, which is probably I have already discussed, but a grid, right? So we just divide the space and that's it, right? We are going to have now information regarding itself. So this is very simple, very straightforward. And yes, variants of grids, like how to use the space, can we group things? All these variants are also very popular. So we are not really giving up on grids. They are simply memory intensive, but they have very interesting properties. And well, finally, the sign distance function. Maybe some of you have already heard about it, maybe not. It's a very simple way of calculating things. So imagine now we will have a grid, 3D grid or whatever, and the value of each of these cells is just the distance to the closest surface. Okay, so here this blue indicates that the closest surface is here, right? And the same goes on, right? So if you start like moving around the line, what you see is this nice gradient, right? So this is a little redundant. We are encoding here a lot of information just to say that the surface is like this. But at the same time, this allows to have like a lot of details, right? So what is happening when you are close to here, right? So distance, maybe it's equally close to this point and the other point, right? But with this representation, we can have also very detailed surface structure of 3D 3D objects or 3D environments, right? So this is also very used. It has advantages. There's like other operations that can be done like very easily with SDFs. And we also have the truncated version. So here what I'm plotting is just the value. So the truncated version, what it's doing is take a look at the vicinity of the surface, right? It's just truncating values up to some threshold, right? So it means that it's just measuring like how far away a surface is up to some threshold, and then things are constant, right? So why is this? Well, this has some advantages. We are not going to be discussing them, but this is also a very popular 3D well, surface representation. Okay, any questions so far? Any comment? Who has seen like some of these representations before? Maybe some paper you read, some other course? Okay, SDF is new. Okay. Yeah, I mean, I didn't define it formally, but well, the intuition is just this. How far away is your surface, and what is the closest distance to this surface? Okay. Good. Oh, we have another question. GCV course is about this, I think. GCV is General Computer Vision. Geometrical, yes, geometric computer vision. Okay, got it, yes, awesome. So then you discuss about 3D volumetric representations and surface representations and all this, right? Well, I guess that's a yes. I thought geometric computer vision was more about epipolar lines, key points, and you know. Okay. That was the first lecture. Yes. But you are right. So there we have on the catalog of courses, a course just describing like probably more in deep all these 3D representations. Okay. Well, that's good to know. Let's move on to this first step, I think, on mapping. So with this, you will get like a little intuition of what mapping means. This is, by the way, described in chapter 9 in probabilistic robotics. So if you want to take like a closer detail or especially get derivation, you have that there. So let's start just with giving an example, right? So this is a very popular technique. As you see, there's nothing explicit here. So basically, this is just a grid of many, many points. So in this case, this is an image. But, here, without explicitly saying which are the lines, which are the corners, which are the walls, we see that the structure kind of looks like, what is this? Kind of like an indoor environment, some sort of corridor. Well, we don't know quite well, but here in this example, what you can see is that zeros, the white values, right, on the grid, encode free space. And values of 1, this is the black pixels, encode objects, right? Or basically something that the sensor has detected as an object, right? It could be a wall, it could be something else, right? But at the end, there's something that the sensor is detecting. If you're just looking at distance to the nearest object with some sort of LiDAR, then you will get like these readings telling you, oh, there's something in front of you. Okay, so this is a little the motivation. And then what is this gray area? We will define later, but this is undefined, right? We haven't observed, we cannot say anything. Here it could be like a solid wall, or it could be free space. But with our readings, we cannot really do this. Okay, so this will be the result, our aim after, just updating our map like several times, maybe from different positions. But what we know for sure is that we need positions, right? Okay, so let's describe this a little more formally, right? Let's start with the simplest kind of way of analyzing this. So imagine we have a 6x5 map. So these are just small cells, not a lot. And then if we really want to calculate, remember that our final objective is always just giving a probabilistic description of this map with respect to the observations we have and with respect to the position, then we need to analyze this properly, right? So the first thing that comes to our mind is, okay, what are the variants of this map, right? So we have in the map all these cells. We could be defining this as a set of cells, right? So here maybe that's where we have like the connection with point cloud, right? But this cell now has like neighbors and there's some similar structure, but it's not exactly like a point cloud. And each of these cells, right, could be occupied or free, right? So we have like, okay, let me put it this way. So we have, okay, you imagine here there should be 5, but okay, I didn't put them. And then the question is going to be, is this occupied or is this free, right? So this is the only thing we are defining with this set of cells, right? Declaring if it's either occupied or free. Okay, so if we do it this way on brute force, the proper effect of analyzing all chances, remember that this is going to be a distribution and we need to have a probability for each of these outcomes, right? That would be the definition. But then let's take a look, right? So how many possible maps do we have out there, right? So just for this small grid of just having like some points here, the combinations are huge, right? 1,000 millions. That's a lot for us to analyze. But okay, let's say that maybe machines are very fast. Now, if you think about it, the map that I was showing you before, it was probably 100 by 100 or even more, like 400 by 400. And when we have this, then the number of combinations is simply intractable, right? So let's forget about it. It's not going to be possible to do proper estimation of this probability without doing some assumptions, right? So that's what I'm defining here, like some assumption. So let's take a look at them, right? The first one is something that we have used before on observations, right? So this is cells are independent. What does it mean? Well, it means the following. We have a cell here, right? And the result of this cell, it's going to be independent of what is next to it. Now, we know that this might not be true, right? We know that maybe if there's an object, it's more likely that there's a cell with an occupied result next to it. But the assumption, and just for calculations, is just saying this, right? That at the end, this joint probability of all cells, right? It's just going to be the productory of all observations. This is just to make things tractable. So we know that when things are independent, these combinations are simply not necessary. And then what we calculate is case by case, what is the value, right? So from exponential complexity, we have gone just to linear complexity. But although this makes things tractable, it also removes part of the information that we might be getting here. And this fact simply goes away. If there's an object here, it's not going to be saying anything about what is next to it, what is close to it, nothing, right? It's just going to care about this state of this current cell, and that's it, right? So this is something important we are giving on, right? Or with grid mapping is giving on. Yes, and the second approximation is that it exists an inverse model, right? Such that if we give an observation, right, it's gonna be giving us like a basic kind of likelihood of what is the probability of each of these cells, right? And I'm gonna discuss on this like a little later, but this is important because otherwise we would have here the same problem, right? If we don't have an inverse model of some observations, then it's hard to define this term, right? We need to do like proper things, and we know that with cells, with so many options here, it's basically complicated to relate to this relation of observations and what is the effect to all cells, keeping tractability or complexity to some reasonable bound. Okay, so with these two approximations, then I will show later that just calculating this belief on the map, it's tractable. It's gonna look like a filter, you will see, but it's definitely something that we can do very fast. And remember that this is the first technique we are discussing. Well, there's others that are taking other considerations into account, but well, this is very popular technique, by the way. It's still being used on some problems. So maybe if you, I don't know, start using like some packages out there from ROS or something, there's definitely going to be variants of this. And the representation is the same, right? So occupancy grids. Okay. Let's define a little more properly, like what is this binary state? We have already commented that we either have free occupied, but what if we describe this as a random variable, right? Instead of just being a state, let's now describe this as a random variable, and then we'll have like the following probability, right? Because it's binary, it's only two states, right? But the probabilities might giving us like an idea of what is this state, and we'll have the same, right? So we'll have probability 0 for the free cell. We have probability 1 if it's occupied, and then what is in between, there's going to be no knowledge, right? So if you want, this probability is just calculated as the expectation, right, of this either free or occupied, and with this we'll have like value, right, of this random variable that goes from 0 to 1, right? So this was something we discussed at the beginning very briefly, but now let's take it this way, right? So we are going to have something like this. Now, probability is describing if either this cell is free or occupied or in between, right? So what is the problem of that? We have like binary things that are going to be 0 or 1, or maybe very small numbers, very big numbers. There's going to be here some issues, right? Some numerical issues. So imagine that you want to change from 0 to 1, right? So that means that there's going to be a product of probabilities. Depending on the value of your 0, you might not be updating things correctly. So imagine you multiply something by 0, or maybe there is roundoff error. It doesn't matter, right? But it's a little more convenient, and this is justified in the probabilistic robotics, to instead of using this standard PDF, to use this alternative, which is totally equivalent, but alternative definition of these binary probabilities, which is called log odds, right? So log odds is nothing else than this ratio, right? The probability of being, in this case, free, divided by probability of being occupied, right? Here, because there's this duality, we know that, well, one is just the opposite of the other. So that's why we can write things this way, right? There's only two states, basically. And then once we have this ratio, the log odds, what it's saying is that instead of keeping this probability in the range of 0 to 1, then we define a logarithm over this ratio, right? And what is the advantage of this? Well, the advantage is that if x before was only in the range of 0 to 1, right? What we have now is a new function that it's a little more descriptive, right? So in this case, we are going to have like the logarithm, right? That is going to be saying that for values that are very close to 0, we are going to we will have numbers that are negative, and they keep decreasing, right? So basically, they go up to minus infinity. At minus infinity, we'll have the 0. So we never reach exactly the probability of being 0, which is right? With noise, we can not ever be certain, although that looks a little strange, but we know the effects of just considering randomness. And the same happens for unoccupied. We will not have perfect certainty. What we can have is a number really, really close to 1, right? And this is in logarithm. So in this case, this is going to grow up to infinity. So what is the advantage? That, for instance, imagine that here you have your P of x, which is very, very small, right? So maybe not like 6 zeros or 7 zeros like this, but maybe 30. And then we know what happens when we filter. So basically, we need to start multiplying probabilities. So our prior multiplied by our likelihood gives, well, kind of the posterior belief, roughly speaking, But on the other hand, when we do multiplication operations in logarithms, they are just going to be summations, right? So here, I don't know, we'll have like -7 or whatever it is. And then when you multiply by this probability of, I don't know, this is going to be a multiplication. Well, here, what we know is that we are going to have a summation, right? So you will see it later. But with this, basically, we have an easier way of keeping track of what is the current state without getting into numerical problems, without, other issues. So in general, I would say that, yes, every binary state, it's better to be described with log odds. And in the particular case of occupancy maps, it's also true, right? Okay, so I already give like some hints, but if we do this, can we then revert these log odd probabilities and calculate what is the real probability? of the cell being occupied or not? Yes, we can. So there's an inverse function, and it's simply this, right? So this is a unique mapping, bijective mapping. There's a single value of L that corresponds to P and vice versa, right? So this is great properties. At the end, we might prefer doing most of the operations in the log space. And then if we really want to calculate probabilities, then we can always revert. But for updating the filter, it's going to be more natural to just work in logarithm side. Okay, and this is where I'm gonna skip. Where I'm gonna skip part of the derivation, right? You have this in Prop chapter 9, but the derivation goes as follows. We have a base filter, right? And then we know that the states are binary. So the solution is just taking into account this, that we have an inverse model, that we have a previous, and then we have like a prior, right? So it's just redoing the derivation of the base filter that we described before for the Kalman filter. Do you remember like lecture 4? This is a long time ago. But we are redefining the base filter just to take into account log odd probabilities, right? And just this inverse model on the values of the cells, right? So with a little bit of, derivations, we can get this very compact model, right? So we have some observations and we know the positions, right? So this is given. So the resultant base filter, it's gonna be saying something that is very familiar to us, right? It depends on the previous state. So whatever was the previous log value, it's going to be here. Remember, this was like, after we calculate a belief, right? This is the initial point for the next iteration when you keep calculating, right? So this was a recursive filter. We see the same principle here. So there's still like a recursive form, okay? Nothing surprising. Then what is a little surprising is having this sort of inverse sensor model. So you can think about it as a way of having the likelihood, but it's not exactly like that. I'm gonna give like an example in the next slide. And then this extra term that appears just because we are using log odds is the prior of occupancy, right? So this is the log odd of the initial prior P of X, right? And it's always going to be here. It's always going to appear every time that we update. Okay, let's give some numbers, right? The question is, should I be giving this here or later? Yes, I think we can give it here. Oh no, on the next slide. Yes. Okay, so the only element left is the inverse sensor model, right? And what is this? This was one of the assumptions, so it must be something that it's not so straightforward, right? But the motivation comes from the physical perspective. So the inverse model, the only thing that it's doing, it's relating observations with these updates that we will have in the model. Imagine that we get here this observation, right? This is the observation. So what we get is that in front of the robot, that remember, we know the pose exactly. This is given. We know exactly the pose. With this, we are getting this observation. So if it's the range and varying example that we had before for, I don't know, observations, or if it's like distance to the, or this is a LiDAR, we don't really care, right? But what it's saying is that, look, you have an observation here in, I don't know, this is 2 meters or 3 meters or whatever. So what the inverse model is doing is with a single observation, it's giving information about all these cells that are in this line, right? So you can imagine this as a process of ray tracing. We have here a sensor. We know that the observation is telling us that there's an object in some distance. So this implies two things. The most obvious one is that, yes, you have an object here. So we are going to be returning that, hey, according to our sensor, the object is here. Or maybe the sensor is giving us like this point, right? So we might want to update the map also. But we know for sure where this object or this reading of there's like something that, I don't know, if it's a LiDAR, the light has returned like from this position, right? Or after this time of flight. So there's an object. But the second more subtle thing is that if there's an object here, it means that all this space is clear, right? So we don't have a single observation. What we have is several of them. The most obvious is, yes, we have like some reading of that there's an obstacle here and the sensor is not really getting through. So this usually is used for LiDARs, for I forgot the name, ultrasounds, and this kind of other sensors that are just, projecting like some signal, and then they are just reading the return, estimating what is the time of flight. But it's also equally important, right, that all these things on the way, they are free, right? So this is all it means, the inverse sensor model. It's some sort of ray tracing just to distinguish which cells are occupied and which cells are free. Okay, what happens here? What can we say about this? Any idea? Okay, we cannot say much, right? So, yes, undefined, exactly. Yes, exactly. And in terms of the filter, this is very easy. So you don't do anything. You just keep whatever you had before. Okay, let's start with these two cells, right? So here we have M1, that is this guy, right? And here in blue, we will have M2, which is here, okay? So let's do this. Previously, M1 and M2 were free, right? So this was before getting here. Let's say that our map was saying, yes, sure, you have like a total free values here. So let's go with this, right? So then it means that at this instant of time, this one cell, well, at the previous instant of time, yes, this cell was had a log odd value of, okay, well, not free, but with 0, we can say that this was undefined. Remember that the logarithm, if we have something like this, and we are saying, okay, so if it's 0.5, right, we don't have like any clue, this is going to be 1, right? And basically we have here the logarithm of 1. So in this case, the log odds of 0 is that the exact point. We don't have like any clue of what's going on, but we had this, right? So in this case, let's do the current estimate for LT1, right? So what we have here is LT on the previous state. We have the inverse observation, and then we have L0, right? So how does this look like? We said that before this was undefined, right? So what we have here is a 0. Let's talk about the inverse model, right? So here, M1, it's basically saying that this is free, right? So if this is free, maybe the value is, I don't know, this depends on the sensor. I have no idea, but let's say that this is -10, just to give a rough number. And then what is L0? We can say that, I don't know, for this particular problem, L0 was 0, right? It's perfectly balanced like the prior, but if it was not, then we should be accounting this here, right? So it's going to be like some number. So our new value, it's going to be -10. Okay, let's go for M2, right? So for M2, we have kind of the same problem. The previous step, the value of this was 0. We didn't know anything. We didn't know anything at all. So the only thing we can do is, with this new observation, calculate this. So we have this, the previous one. The inverse model, maybe now that there's an object, it's going to be +10, right? And then the prior is 0, right? So then this is how the update is going to look like, right? If we do this many, many times, you can imagine that here, if we persistently observe that there's an object here, okay, yes, that there's an object here, then yes, this value is going to be high. Imagine now that we come again, and from this position, we do the same, well, ray tracing of this observation, and then what we see here is that this actually was free, right? So then what it means is that this ELT plus, I don't know, some horizon of these two, it's going to be this, I don't know, in this case 10, minus, I don't know, 10 or whatever, right? So in this case, there's a balance, and we are not directly multiplying on the 0, 1 space, right? Which can be dangerous if you do this many, many times. But with this, we are filtering. We can compensate for observations that are persistently observed as free, right? So they are going to remain free for some time. And when you have new observations, it's easy to come up, right? So imagine that you have just a new object here that is put there, then the method can also overcome this, right? So maybe, I don't know, you set a threshold to, well, yes, but basically new updates are just going to take into account this value. So if you have enough observations of this new object, you can revert things in your map. It might take time, right? It might take time until you, I don't know, whatever value is that you have estimated, this very large negative could change, but eventually you will, right? While if you have a lot of multiplications of very small quantities, maybe you just get numerical instabilities here. So then you just get a real 0, everything just gets multiplied by 0, gets clipped, and the update never happens. Okay. If you want to take a look at the derivation, as I said, in chapter 9, there's like in-depth explanation. But I think for now, this is going to be all the explanation on the occupancy grid map. Anybody has any comment or something? Has anybody used, like, I don't know, ROS packages using grid maps? Yes, Gmapping, yes. So Gmapping, it's not exactly this. It's also doing SLAM, but yes, the result, it's going to be a map like this. Oh, do we have occupancy grid map? Maybe this is a typo, yes. Okay, you can call this how you want. Maybe this is occupancy OC, but yes, I wanted to write G. Can we use the map in log space? You can, but take a look that this finally becomes an image, right? And in this grayscale image, things are only well defined if you are in a range of, I don't know, 0 to 1 or 0 to 255. So at some space, you cannot really use the log space for visualization because the image have, I mean, best way of using two-dimensional occupancy grid map is just with grayscale images, right? So at the end, I think, yes, you need to revert probabilities, but you don't have to do this every time. So this is the only, well, the good advantage. We have another question. How we got 10? I mean, why not other number? Yes, yes, I totally agree. 20, right? And maybe here when we see occupation, we have 50. I don't know. That depends on your inverse observation model. So this is going to be whatever you define it there, right? It's not written. I mean, I'm just giving here like random example, right? But the derivation, the proper derivation is in the book. So, but what it means is that there's going to be a value after calculating this logarithm of occupied and not occupied. And definitely negative numbers are leaning to 0, right, of free, and positive numbers are leaning towards, okay, more occupied, right, just increasing the probabilities. But yes, absolutely, this is part of the tuning. And in fact, maybe this number depends on what is the certainty of the sensor. So it's not, I'm not defining this as 10 is it's always going to be the value to use, but it will depend on each case. Yeah, good question. So let's give an example of this. You are very certain about things, then this value could be very large, right? So you update things and then they are going to stay like this way, and you are going to be very certain. If you are not very certain and you need several observations, maybe this value is going to be smaller. So this is a little trade-off here that is happening. Okay, good. So let's move on. Here, wait, does anybody want to do a break? Yes. Let's do a break of 5 minutes, right? And we'll be back with this. Yes, I have like still some slides, but I think it's better just to have a break, stop for 5 minutes, and then yes, we will retake this. All right. It's time to get back. Is people around? Okay. Okay. We have 3 classes. I hope the rest of you are just complaining, not really. You're here, not sleeping. Okay, we have plus plus. Now I like this more. Okay, let's get back to this second part, where we are going to be discussing a little more mapping, more modern mapping approaches. So if the occupancy grid map is kind of a recursive filter, right? So this is very similar to how we define things at the beginning of the course with filters, right? So we know that base filter is basically the basic framework, and then many filters come from here. So we derive Kalman filter, particle filter. The binary filter as well can be defined this way, right? And this is what we did for the occupancy grid map. So for this, remember that cells were independent, and every time that we get a cell, we update its value, right? So on this nice and compact recursive summation, so you just sum the previous state, the previous log odd value plus plus the inverse observation function, and that was it, right? So that's very easy. It's probabilistically sound, right? It's considering noise, so this is an advantage. But maybe there's other ways of doing things, right? And the motivation for some of these approaches is the following, right? Instead of calculating like this posterior belief, which can be intense, if we haven't done this approximation on the independence of cells, then this probability, it's not feasible to be calculated. We cannot really calculate what is it for all different combinations of map cells. It's not tractable, right? If we haven't done this, then what? What can we do with this? It's kind of complicated, right? So there's another alternative that still, it's based on some assumptions, but these assumptions might be a little more reasonable, right? And with this, we will get, I think, more general approach, right? So if independence assumption, it's only possible for some grid representations, with this approach, it's going to be a little easier, right? So the assumption is the following. We assume perfect localization, right? And then we marginalize poses. So what does it mean? That when we calculate this probability here, right? Of okay, you have also noise on your state, right? So you should be accounting for this. Then inside, what is happening is that no, we actually don't have this noise. We are going to assume perfect information about this state, right? And this is done if you can do this if you have like very good sensors, right? So if you have very precise sensors, you could just be doing like this tracking or just calculating very precisely your localization. And if you have this, then this assumption is true, right? So here we are just marginalizing poses, right? We calculate the pose, we align this with respect to the map. And once we have this, what we have is simply a delta function, right? So this is a little the formal part, but if you want a little more description of what's going on, right? So we can forget a little about the probabilistic approach, right? And the result is the following, right? So we have high quality sensors, and the only thing we are doing is So this on these high precision sensors, what we can do is camera or sensor tracking, right? So that is with respect to your map, with respect to this current orientation, with this current observation, it could be a point cloud, it could be, I don't know, whatever observations we have, but we assume that we can align perfectly, and then we assume that this is in fact like the true position, right? So we know that this is a probabilistic approach, but in this case, we are doing this little assumption. Okay, so this will simplify things. Now the mapping problem becomes a little easier. There's no poses because we are marginalizing all of them, right? So when we start doing this iteratively, see that here there's no poses. We have marginalized this, and when we do this again, we are going to be marginalizing, and it's always going to be marginalized with respect to the map, right? So how is this really happening? So we start discussing like things, for instance, for the case of point clouds, right? For a point cloud, in lecture 14, we were saying we have a pair of point clouds. And then what we are finding is a transformation between one to the other. But that problem was the scan-to-scan problem, right? So we had a pair of point clouds, both of them from observations, and then we just find what is this transformation between them. Now, what we are defining is slight variant of this, right? So instead of having a scan to scan, now maybe what we have is a scan to map, right? So what is a map? We said that a map could be a point cloud as well. It could be a voxel, it could be a grid, TSDF. There's many representations of the map. But if we get like some observation that usually it's a point cloud, right? Or maybe it could be another thing. And instead of aligning with respect to other observations, while we align this directly to the map, then this will do the trick, right? And there's many variants of this, there's many ways of doing this. It all depends on the map, right? And there's a second variant also for doing this, which is map to map. Maybe we aggregate all observations into small maps, right? And then the only thing we are doing for alignment is this kind of mini map versus whole map, right? But at the end, what we should get is a very precise solution of where all this information has been obtained, right? If we have it things this way, we can assume that this assumption of perfect localization is true, right? There's still going to be limitations. Actually, some of these techniques talk about this. But still, this will simplify a lot the calculations, right? And with this, actually, we've seen techniques lately proposed that can achieve real time, right? So which is something very remarkable, because if you are doing mapping of all the possible states on these more complex structures, this is very complicated, right? Especially when you perturb them with respect to some values, right? So maybe the best thing is just forget about distributions. You don't propagate uncertainty. You just have there like all information aggregated into a single representation that is just like a map. Okay. And then the very interesting question for lecture 15 in our course is then, if this is true, if this is working, why do we need SLAM, right? So why have we discussed like for 4 or 5 lectures, why, I mean, what is SLAM, variance, then why do we need this? And it turns out that we still need this, right? So we'll see that, okay, this is an approximation of, calculating perfectly the alignment with respect to the map. But still, if you do this over time, you are going to see problems, right? Like drifts and other artifacts. So eventually, if you really want to do like larger maps, not just very small and very loopy maps that you are observing all the time the same thing, but if you want like larger areas, at some point you need to consider a SLAM one way or another, right? And it doesn't mean that you're going to be considering a SLAM as a postgraph or as an iterative process. But what SLAM means is that we still can update things, using previously observed observations, right? It could be parts of the map. It could be other things. So in essence, or one of the essence of SLAM, I think it would be loop closure. So how can we deal with this kind of problems, right? So when we see a loop closure, this is not really going to be affected. It's just going to create a lot of artifacts. Well, SLAM gives us the tools just to correct and compensate for this, right? So some of these techniques that I'm gonna be briefly introducing now take SLAM into account. So it's still necessary. It's simply defined on a different way just to keep real-time conditions like bounded, right? Okay, awesome. So let's take a look, right? Let's take a look at some of them. On this, by the way, each of these methods has like a lot of variants. So I'm gonna start with this because at that time, this was like really a really impactful paper, right? Kinectfusion. I think still today, there's still like variants of this being published, right? At that time, you know, the Kinect camera was released and everyone was very excited because for the first time, they were getting like depth information from a cheap sensor. I mean, time of flight cameras have been around for a long time, but they were very expensive and people were not so, well, they were using them, yes, of course. But let's say that just with the Kinect effect, many new papers appear and this found like, well, all these new papers that I think this one is a very representative one, right? So what is the idea behind? And I'm just gonna explain this very briefly. If you want to take a look at the paper, you have this in Canvas, or you can just take a look, I don't know, Google Scholar or somewhere else that you look bibliography at. Okay, so I'm just very briefly introducing this. There's a lot of details that I'm not gonna be talking about, but the idea is that the model, I mean, the environment, these little scenes are modeled as TSDF. Remember that TSDF is this function that we are measuring all the time from each cell in this 3D structure, 3D grid. We are measuring what is the distance to the closest surface, right? And the truncated version, what it's doing is at some point, at some distance, is saying, look, it's far enough. Just have here a constant value, right? The threshold value. Okay, so then what we see is that here they are doing this kind of principle we were saying. There's not a full trajectory optimization going on. There's nothing like that going on, but it's just doing frame to frame, right? And then at some point, cameras are being localized with this model now it's a little more detailed. This, by the way, it's not a TSDF. This is the rendering of the surface resultant on the TSDF, right? But if you take a look, it looks very detailed, right? There's still like some holes. It's just because the camera has not taken a look from all points of view, right? But definitely the structure looks very detailed. All the surfaces look very detailed. And they are just updating this TSDF. They can do this very quickly by using GPU. But in general, well, let's say that TSDF, it's not that easy to update if you're just using a standard CPU. What else? So there's no trajectory. It's all the time the map structure, TSDF, is being updated, right, with these new observations. And the results were very, very good, right? So you can get like this level of detail, which is amazing for first generation of Kinect. You know, Kinect is very noisy and has some artifacts, and they were just only using that. So this is a highly cited paper. There's many variants, many follow-ups. Really, I think it was impactful at that time. This idea of just doing frame to frame, or let's say just forgetting about the full trajectory and just doing camera tracking, it's not really original from here, right? So we will discuss tomorrow on Vision SLAM that this has actually been a very important contribution on the field, right? Just to make things real time, you know, so with the effect of keyframes. But let's say that this thing of just assuming perfect information is a way of keeping real time. If you had to calculate the trajectory and all the map. And the map, how can you perturb, I mean, if you perturb the trajectory, how this affects the map, then this thing becomes like very complicated. Complicated in terms of calculating a solution in reasonable time, right? So still, the results were very good. So this is something that we should be, well, getting the idea that still, if you have a sensor, it's possible just to do this assumption and still you would get very good results. There were some limitations though, so that's why some of the follow-ups were. And basically you have this grid, right, with your TSDF. And the limitation, the size, it's going to be the GPU, the memory that you have on GPU, right? So if you want a new sensor, then you need to load a lot of data again. And this, well, at least in this work, well, they were just defining this for small sensors. But yes, some other researchers have been investigating how to enlarge this to more sensors, to large scale, to consider, I don't know, like, so this is possible to do. Okay, great. So take a look if you can. Let's discuss now about the next paper. Some of the authors are also the same, so I guess this is something very remarkable. Let's talk about Elasticfusion, right? So in this case, the map representation is surface based. So what is a surface? You can imagine that a surface, it's kind of a point, but this point has planar properties. So instead of being just a point with no dimension, it's kind of a disk moving in the world, right? So here you will have a normal, and then you will have position, right? And then you can have many of these guys all around. If you have enough of them, like very compact, you could have like something as detailed as this, right? So here, I think the authors were reporting like millions of surfaces. So still that's heavy, but this is a little more flexible structure to work on. So TSDF, it's a little less clear where you have your surface. So you have to process things. You need to render surfaces. But with this directly, you have like implicit representation of all these surfaces by all these little disks, right? So here they also have a radius, right? Okay, so what do you do then? In this case, they were also using color. So imagine here the surface could also be like this. So you have position, you have normal, you have radius, and you have color. You have a lot of information. Still, I'm considering this part of mapping and not Visual SLAM because they do a very interesting update, right? I'm going to discuss it like just now. But then once you have this map of surface, what you are doing is just calculating what is the camera alignment with respect to your map of surface, right? And for camera alignment, I mean that they were using RGBD, right? So it's color, so there's going to be some photometric error, and there's well, I think the loss they are using is not photometric. I need to check this, but definitely they are using color, and most importantly, they are using depth, right? And with depth, you can calculate point cloud alignment, right, between your sensor and your map. So this is well, another way of looking at this. Then, once you have calculated this exact position of the camera, what they do is they just do fusion of surface. So that's why they are calling this fusion, right? And what it means that they are updating some of the surface that they know that they are being not exactly matched, or if they are adding this new information, right? So if you have little variations, this could help, right? But interesting things happens here when you have loop closure. What happens when you have loop closure? So imagine that you have some drift, you have a map that has not really corresponded. What they were creating is a function just to keep as rigid as possible things on this kind of set of surface. And maybe on this loop closure, there was some drift. So imagine that there's some elasticity between this set of surfaces that when you update some of them just to be fused, that means fused by a significant amount, like not small update, but really like, I don't know, centimeter or something like that. This loop closure is dragging all the map structure, right? So that's what they were calling this elastic, because they were defining elastic loss function when they were doing this update. But the interesting idea is that they are not doing this with a post graph, right? So this is not the result of, it's equivalent, it's similar. So at the end, the optimization might have similarities, but because there's no trajectory here, there's no trajectory, there's nothing. I mean, these surfaces are in the same common frame. They cannot be related back to any position. So you cannot really update your trajectory and then update all map. So you need to update directly the map. And for doing this, you just need to look for this elasticity that preserves the structure that they have obtained, right? So imagine if you have here like this table here, and you're observing this, so everything will be moved a little, you know, like in this, and that's why they were calling this elastic. So this was like very interesting. This actually has been like ideas similar to this have been in graphics, like elastic kind of functions. They were published like a long time ago, but okay, because the advancements of the time were not like that. So that those papers are, I mean, I'm not talking about them. I'm just talking about this, about the Elasticfusion from 2015, because this also spanned like new kind of generation of papers, or there were many follow-ups, many things to analyze this, but it was not, I mean, some of these things have already been developed like before, especially the elastic cost, right, among surfaces. So, okay, still, very good. This is definitely a reference paper. Take a look. It's inside Canvas as well. You can also check the videos, right? So maybe with this, you will see a little more clear idea of what's going on. And let's analyze now the last example. So all the previous ones, Kinectfusion and Elasticfusion, they are using some sort of RGBD. So these are sensors that are giving you color, but also they are giving you dense depth representation, right? So you have a depth image, and by density, it means that points are very close one to each other, right? In this other approach by Zhang, called LiDAR odometry and mapping, they are using LiDAR, right? LiDAR with, I don't know, 3D LiDAR or just moving LiDAR, but the properties of this kind of point clouds are different, right? So you don't have dense point clouds, right? So you need to do other things because remember in our example, so when you have a wall and your LiDAR is, what they had is different bins, right? So you have different bins, and for this, yes, you have a lot of points, but there's like some inequalities on the density and dispersion of points, right? So a lot of points on this bin, but not really much here, right, in between bins. So still with this, the authors did also a very, I think, reference work, right? Their map representation now, they are using voxels. So voxels is a way of decimating point clouds equally. Imagine if you accumulate thousands of these points or millions of these points, these can become tricky at some point, right? So voxel is just a way of, you know, keeping structure a little more limited. Still, this is an implicit representation, right? We could have like different number of voxels, but still for efficiency, this is some consideration to take. And then there's a second thing, and that they were just dividing all these huge voxels into into subdivisions. So depending on where you are, not all map or not all voxels in the whole map are needed to be used, right? So this is a way of just, loading like part of the data without using the full map, right? So this was just a trick, but still, for efficiency, it can work well. Why? Because they are doing this for long-term or large-scale maps, right? So imagine if you are here, maybe this section is not useful, right? So you will never see this, right? So why do you want this? There's no need. Okay, still, what is the essence of this work, right? So what is the thing that they are really doing just in order to make this work in real time, right? So this is, well, the first thing is they have a high frequency alignment of odometry. So imagine this would be like similar to the point cloud alignment we were doing on the last lecture, but you do this very with high frequency, right? So that means that at every new observation, you want to calculate a solution, but you don't have all the time in the world just to have the finest and most detailed solution, right? You just want like some coarse approximation of how your odometry looks like. And then there's a second thread going on, right? That is happening at a less frequent rate. And what it's doing is this scan to map, right? So, and this is a more detailed operation. So imagine from this detailed map of voxels, you have your observation, and then you are doing registration with respect to this. And if needed, you also update the map, right? So this is, well, this kind of two, yes, it's combining like those two different processes. Note here that there's no estimation of trajectory, right? It's always the same. It's this trajectory has just been marginalized, and what we have is a global map, right? And when we calculate a new pose, first of all, we are going to be calculating what is this transformation. And then once we have this, we just update things in the same reference frame. So there's no pose here to be calculated. And here, well, you have some examples of LOAM. It actually works very well. Yes, so either for indoors or for outdoors, right? It's kind of amazing that here in outdoors, they can obtain features because, well, this is something that I didn't describe, but inside they are using line and planar features of small vicinities. And with this, they are doing the alignment a little more fast or efficient, right? So they are not combining all points against all points, right? But still here in outdoors with practically no regularity on surface, all these, well, leaves, this is still, they are getting very good results, right? So this is the map that they get, well aligned. And for indoors, well, it's also like very remarkable results. Okay, so this was all techniques that I wanted to discuss today. It's more like an introductory material for mapping. We have discussed occupancy grid map as kind of the reference. Some techniques are still based on this and this way of updating cells, this recursive way of updating cells. This is still being used, right, with log odds in maybe more advanced maps. But there's also this trend that I think it's very interesting of just marginalizing poses, and then you just update maps with your observations as they are, right? Problems with this is drift, mostly drift, right? And that's why, for instance, Fusion was, just updating the map on a way that it was equivalent to do pose update of all your trajectory, but at the map level. And well, there's other techniques also that people are using. But yes, now with this, you can take a look at the papers, and many of them, many other papers, many other publications are, have some reference or have some peculiarities taken from, I think, some of these papers that we have discussed. Of course, there's more, right? So I cannot really do like a total literature review on this topic, but I think as an introduction is good enough. All right, that was all for today. Thanks everyone. Tomorrow we will be doing another introductory lecture to Visual SLAM in this case. So we will also be discussing some techniques and other things. And I'll see you tomorrow. All right, goodbye.